Everyone. This lecture is mainly about uh, damped free vibration, which is another type of vibration. In the previous lecture, we discussed about undamped free vibration. So, before this lecture, we will summarize the previous lecture. In the previous lecture, we mainly covered vibration or uh, which is also we call is oscillatory motion. We discuss different type of vibration, that is free and forced vibration, and also damped and undamped vibration. So in the previous lectures, we discussed mainly about the undamped free vibration, that is how to derive the equation of motion for undamped free vibration, and then how to solve these equation of motion, and how to then plot these equations, and then we also solve a variety of numerical examples based on undamped free vibration. In today's lecture, we will mainly be concentrating on a damped free vibration. In this course, we will not be discussing about the force vibration. So we also discuss about the degrees of freedom. So the degree of freedom of a dynamic system uh, is the degrees of freedom which is required to completely specify its motion at any instant of time. And as we can define the dynamic system, so we can say that it is either discrete or continuous. So if it is discrete, so then we can simplify the dynamic system, and we can say that the system is having finite degrees of freedom. On the other hand, if it is a continuous system, so it can have infinite number of degrees of freedom. We also then discuss about the periodic motion, which is motion which repeat itself after certain amount of time, and that amount of time is what we call is time period. We also discuss about simple harmonic motion, which is type of periodic motion. uh, and simple harmonic motion is a simplified version of periodic motion. So in simple harmonic motion, the displacement is represented by this simple functions, which is sine or cosine. So as you can see, this function here is x equal a sine omega t, and here you can represent this function or on the x y plot. So on the y-axis we have displacement x, on the x-axis we have time, and we can plot this sine function here, and a here is the amplitude of vibration, and we can say that this a is the maximum displacement from the equilibrium position. So or on both sides, so on the negative side or on the positive side. And if you want to derive the equation for the velocity, so you will just differentiate the displacement with respect to time. So you will get this equation here, so cos omega t omega a. In this case, we can change this cos omega t to sine omega t plus 90 degrees, or pi by 2 radian. So this means that the velocity is leading the displacement by 90 degrees here. And similarly, you can calculate acceleration by uh, differentiating velocity with respect to time. And this, if you want to get rid of this negative sign here, so you will just introduce this pi here. So this means that this is sine omega t plus 180 degrees, or pi radians. So if you plot this velocity and acceleration on the xy plot, so these will look like these. And in this case, the only difference is the the amplitude here. So in this case it is omega a, and in this case it is omega square a, and this is velocity and this is acceleration. We can also represent these with this plot here. So in this case, the if this is the displacement, so the velocity is leading the displacement by 90 degrees, and similarly the acceleration is leading the displacement by 180 degrees, and which is this 90 degrees or and 180 degrees. Now then we also introduce how to write the equation of motion for the undamped free vibration. So this is the schematic representation of the undamped free vibration. So in this case, it is represented by a spring and a mass. So mass is attached to a spring, and this is the equilibrium position of the mass. So in this position, there will be no force in the spring, and if you give it some displacement and then you leave it here, so it will vibrate to and fro from this equilibrium position. So in this case, at position x, if you want to draw the free body diagram, so then it will have these three forces. One is the weight of the body, one is the normal force of the plane on the body, and another is the spring force, which is kx. And we can write the equation of motion by using the Newton's second law. And because acceleration, if we consider, is positive to the right, so this is the equation of motion, and in this case we have only one force in the x direction, which is negative. It's the force in the negative direction, and so minus kx equal mx double dot. If we simplify this equation, we will get x double dot plus omega n square x equals 0. This omega n is k by m under the root, and this omega n is what we call is the natural frequency of the dynamic system. Now this equation is a differential equation. Now we are interested to calculate the value of the x from this equation. So this is a second order differential equation. So this involves the second derivative of the x with respect to time, and this equation is a linear equation because omega n is not a function of x by itself, and the right hand side is 0, so it's a homogeneous equation. So the equation is second order homogeneous linear equation. So from the mathematics, we know that the solution of this equation is x equal a sine omega nt plus b cos omega nt. So in this equation, a and b are two unknowns, which we can calculate from the initial condition. So the initial condition in this case is that at t equals 0, v equal v1, and x equal x1. So these are the initial condition. If you use the initial conditions, so then we can calculate the value of a and b. So the value of a is v1 divided by omega n, and the value of b is x1. So this will be the final equation for the for the displacement. Now again, we can see that this is a little bit complicated equation, so we can further try to simplify this equation. So this simplified version of this equation is c sine omega nt plus pi. Now in this case, this c and pi are two unknowns, which again we should calculate from the initial conditions here. The c and pi can also be linked with a and b. So we can plot this equation because this is just a sine function. But again, we have this angle here, which is what we call is a phase angle. The phase angle means that this pi angle will shift the sine angle, the sine curve. So the sine curve is should come to this point here, but we have this pi angle, so it is shifting the sine curve here. And so the distance from here to here is pi, and when omega nt is 0, so we get this magnitude here, which is c sine pi, and the amplitude of this vibration is c here. So the distance from here to here is c, and then the distance from here to here is 2 pi radian, which is omega n tau, and the time from here to here is time period of this specific plot. So from this equation, then we can calculate the time period, which is 2 pi divided by omega n. Omega n is the natural frequency in radian per second. So if we put the value of omega n, which is this k by m under the root, so then we get tau, which is 2 pi m by k under the root. And then from here we can also calculate the natural frequency in cycle per second, which is 1 over tau, which is 1 over time period. Okay, so in today's lecture we will mainly be concentrating on the damped free vibration. So therefore we are introducing damping, and we will mainly be discussing three type of dampings here. One is viscous damping, one is Coulomb or dry friction damping, and another one is material or solid or hysteretic damping. But we will be mainly using this viscous damping in the mathematical equations, but we will just introduce the other two so that you have some idea that we can also have these dampings. Now we will discuss in detail the damped pre-vibration. So this means that we will derive the equation of motion for damped pre-vibration. Then we will solve the equation of motion for the damped pre-vibration, and then we will also represent this this the solution of this equation by graphical mean, and then finally we will solve some numerical examples to understand the use of these equations. And obviously the numerical examples and the theory are taken from mainly from these three books. Okay, so first is that what we need to understand is what is damping. Okay, so damping is if you assume a vibrating body, so we know that the with time the vibration of the body or the energy of the body is converting into heat and sound. So this means that this reduction in the energy of the body which is changing into heat and sound, so this will reduce the displacement of the body with time. So this mechanism by which the vibrational energy is gradually converted into heat or sound is what we call is damping. And a damper is assumed to have neither mass nor elasticity. And damping force exists only if there is a relative velocity between the two ends of the damper. Okay, we will discuss this in detail. This is specifically applicable in the case of viscous damping. So it is normally difficult to determine the cause of the damping in practical system. But we can say that the damping can be of the following three types. Okay, so the first damping, the first possible damping is what we call is the viscous damping. Okay, so the viscous damping is when a mechanical system vibrate in fluid medium, okay, such as air, gas, water, or oil. The resistance offered by the fluid to the moving body cause energy to dissipate. Yeah, so in this case, if you assume this cylinder and piston mechanism, and assume that mass is attached here, so this is our mass, and it is just fixed from this end here. So we can see that if the mass is moving, so the piston will move with the mass, and there will be fluid in this cylinder here on both sides of the piston, and we will assume that there are holes in the piston, so the fluid can move from one side of the cylinder to the other side. So if there is a relative velocity of the piston, so if the piston is moving inside the this fluid, so the fluid will dissipate the energy of the piston, and this way it will try to reduce the displacement of the mass. Okay, so that's why we call that this is a viscous damping. Now there's another type of damping which is what we call is a Coulomb damping or dry friction damping. Okay, so which can be represented by this schematic diagram. So if you consider this body here, and this body is moving on this surface here, so if there is not enough lubrication between the two surfaces, so we know that the normal force is in this direction and the friction force is mu n, which is in this direction here. So this friction force is what we call is the Coulomb or dry friction damping, and this friction is actually will reduce the energy of the vibrating system, and this will try to reduce the displacement of the vibrating body. Okay, on the other hand, we also have another type of damping which is inside the material itself. Okay, which is what we call is material damping or solid damping or hysteretic damping. Okay, so when a material is deformed, energy is absorbed and dissipated by the material. So the effect is due to the friction between the internal planes which slip or slide as the deformation take place. And in this case, if you consider this plot here, so this is what we call is the hysteresis loop for elastic material. Okay, so if you apply load on the material, this is stress and this is strain. So if you load apply on the material, so it will follow this path here. But if you unload the material, because there is this internal deformation in the material, so it will not follow this path here, but it will follow this new path which is going this way here. And then if you load it again, so again it will follow this path, and then it will follow this path on the unloading. So there is this area inside this plot, and this area of the loop is what we call is the energy lost per unit volume of the body per cycle due to damping. And this you can understand from this figure here. So again, this is the stress and this is the strain. So again, we can see that during the loading, which is the AB, so the energy that you give to the system is ABD, and when you unload the system, so the energy that you're getting from the system is BCD. So this means that this energy which is inside the loop is actually the energy that is you losing during this one cycle. Okay, and that energy will reduce the vibration of the body or the displacement of the body. Now, if you consider a damped free vibration, so this is the schematic diagram of the damped free vibration. So we represent this with a mass, a spring attached to a mass. But in addition, now we have this another mechanism here, which what we call is a dashpot, which is consisting of cylinder and a piston. So in this case, the main idea of this dashpot is to limit or retard the vibration. And the thing is, it consists of a cylinder filled with a viscous fluid and a piston with hole or other passage by which the fluid can flow from one side of the piston to the other side. And now the thing is that the simple dashpot arrangement is shown schematically in figure. Exert a force Fd, which is Cx start, and whose magnitude is proportional to the velocity, velocity of the mass as shown in the figure. So in this case, as you see, this damping force is uh, is directly proportional to the x dot. So this means that if we have a relative velocity between the two end of the damper, so we will have a damping force. So if the velocity is very low, so then the damping force will be low. If the velocity is high, the damping force will be high. So therefore it is directly proportional to the velocity. And in this case, if you introduce this force here, the constant of proportionality c, so c x dot, and this means that the we have this fd is equal to c x dot. So this c is now constant of proportionality here, but in this case obviously we are using a negative sign to make sure that the c, this force, is opposite to the velocity. And here you represent this by this plot here. So if you plot uh, force on the y-axis and displacement on the x-axis, so we can see that it's a linear function between the velocity. So if you increase the velocity, you are increasing the damping force of this viscous damping. Okay, so this is the viscous damping that we are showing here. uh, and again, from this equation you can calculate the unit for this c. Okay, so because on the right hand side we have force, on this hand side we have velocity, so this means that the unit of this uh, fd is newton, and then you have c, and then you have x dot, which is meter per second. So this means that the unit of c will become newton per meter per second, which is this thing here. So newton second per meter. Yeah. And now again you can see that the direction of the damping force as applied to the mass is opposite to the velocity x dot. So thus the force on the mass is minus c x dot. Okay, as I said earlier. And now if you want to draw the equation of motion for the body with damping, so we will determine this from the free body diagram as shown in the figure. So now in this case, we have this free body diagram. So if you consider this mass here, now in addition to the spring force, which is kx, again this is the equilibrium position for the mass. So at this position there will be no force, but now we are moving the body to a position x here, and therefore we have a spring force which is kx, and we also have now a force due to this viscous damper, which is c x dot. So this x dot means that is cv, or c into velocities. On the y direction we have weight of the body, and we have a normal force which is this surface is exerting on the mass. So in this case, if you want to draw the equation of motion, you will start with the Newton's second law. So summation of all the forces in x direction equal to mx double dot, and we are taking this direction as positive because the mass is moving in this direction. So this is our the direction of the positive acceleration. So in this case you can see that you have minus kx, which is the spring force, then minus cx dot, which is the force of the damper, and equal mx double dot. So as compared to the undamped free vibration, in the damped free vibration we have this additional term here, which is minus cx dot, which was not in the previous lecture, but now we have this additional thing here. So if you simplify this equation, so if you move this kx and cx dot to the other side, so you end up with this equation mx double dot plus cx dot plus kx equal 0. Okay, so now in this case we are introducing two constant. In the previous lecture we introduced one constant, which was omega n, and the value of omega n was k by m under the root. But now we are also introducing another constant, which is, you can say, is the combination of constant, and this is what we call is zeta, and zeta is equal to c divided by 2m omega n. So you will see in a minute how you introduce this constant in this equation here. So if you take this equation here, mx double dot plus cx dot plus kx equals 0, and you divide this equation by m. Okay, so you divide this equation by m, so this m and here m, and you divide this by m, so you get this equation here, because this m will cancel with this m here. So you will get x double dot, and then you get cm x dot, and then k divided by m x. Now we know that this k by m is actually omega n square. Okay, so this is omega n square here, but now this is c by m, but we want to introduce this zeta here. So what we are doing, that we are just multiplying this factor here by 2 omega n, and we are also dividing this by 2 omega n. Okay, now if you just rearrange these terms, so you can see that c and m 2 omega n, so you can just move this term to this side here, and on this side here you will get c and 2 omega n. So now we can see that this term is obviously equal to this zeta. So you will end up with this equation, so x double dot, and then this is zeta and 2 omega n, so 2 omega n zeta x dot, and then you have plus omega n square x equal 0. Now this this zeta is a very important parameter, which you will see in a minute what is the use of this z, and this is called the viscous damping factor or damping ratio, and this zeta is actually telling us the severity of damping. So you will see this in a minute what we mean by the severity of damping. Okay, so now the thing is, we have this equation for this specific system, which is the damped free vibration. So we have x double dot plus 2 zeta omega n x dot plus omega n square x equal 0. So this is the equation of motion, and again we know that this equation is a differential equation, and a homogeneous differential equation, because the right hand side is 0, and it is also a linear differential equation, because the constant, which is 2 zeta omega n and omega n, is not a function of x. So that's why it's second order linear homogeneous differential equation. But now in this equation we have x double dot, and we have x dot, and we have x. So from this equation now we want to calculate the value of x with a function of omega n t basically. So we want to solve this equation to find out x. So this means that x is unknown, which is what we want to find out now. Okay, so to solve this type of differential equation, we know from the mathematics that normally we assume that the solution of this equation is of this form, which is x equal a e lambda t. So we assume that this is the solution of this equation, and this lambda is unknown here, and a is also unknown, which we need to find out. So if this is x, we can calculate x dot, which will become a lambda e lambda t, which this is just your differentiating with respect to time. And if you differentiate once more with respect to time, so what you will get a lambda square e lambda t. And if you put this x dot, x double dot, and x back in this equation here, so what you are getting so e lambda t plus 2 zeta omega n, and then you have x dot, which is a lambda e lambda t, and plus omega n square a e lambda t equal 0. So you get this equation here. Now we know that in this equation the a e lambda t is the solution which cannot be equal to 0. So if this cannot be 0, so this means that the lambda square 2 zeta omega n lambda plus omega n square should be equal to 0. So therefore we are writing this thing here, that lambda square plus 2 zeta omega n lambda plus omega n square equal 0. And this equation is what we call is the characteristic equation. Yep, so this is the characteristic equation. And this is you can see is a quadratic equation, and in this equation this lambda is unknown, which we want to calculate. So lambda 1, so this is a quadratic equation, so it will have two roots, that is lambda 1 and lambda 2, which we can calculate using the quadratic equation. So this is a simple quadratic equation, and from this equation we want to calculate the value of lambda, which we can calculate by using this quadratic equation here. So if you put the value of a, b and c here, so obviously you can see that a is 1, b is 2 zeta omega n, and c is omega n square. So from if you put these a, b, c in this equation here, so then you will get lambda 1, which is omega n minus zeta plus zeta square minus 1, and then you will get lambda 2, which is omega n minus zeta square minus 1 under the root. So you get these two roots. Okay, so this means that now the thing is, because this system that we have is a linear system, and we said that this is the solution of the linear system, but now because we have two zetas here, two lambdas here, so lambda 1 and lambda 2, so this means that the linear system have this property of superposition, which means that the general solution is the sum of the individual solutions, so each of which correspond to one root of the characteristic equation. So this means that the x can be written as a1 e lambda 1t plus a2 e lambda 2t. So this is the solution of the system, because it have two roots now. So therefore we can write the value of lambda 1, which was this thing here, and then t, and the value of lambda 2, which is this thing here, and with t here. Okay, now this zeta, which we explained earlier, and the value of zeta was c divided by 2m omega n. So this zeta is lies between 0 and infinity. So this means that the zeta cannot be negative, it's always 0. So if it is 0, so this means that we have no damping, because c will be 0, so there will be no damping. So when zeta is 0, so then there is no damping. Okay, so based on the zeta, then this equation can be solved in a different ways. So then based on this the value of the zeta, this radicand, which is the term inside the square bracket, which is zeta square minus 1, so it can be positive, negative, or even 0. So this means that if zeta is 1, then this thing is 0. If zeta is greater than 1, so then this means that this thing is positive. And if zeta is less than 1, so then this will be negative. So then based on the value of the zeta, then it's actually yielding these three type of damping vibration. So the one when zeta is greater than 1, so this means that the system is what we call is an overdamped system. So this means that if zeta is greater than 1, then zeta is greater than 1, so this means that uh, this thing here inside the this square root is positive, uh, and this is zeta square minus 1, and this is zeta square minus 1, and this is minus, and this is plus. So this means that the roots of this equation is distinct, real and negative numbers. So then what will happen that the motion is given by x will approach 0 when t is very very high, and obviously there will be no oscillation and therefore no period associated with the overdamped vibration. So in this case, because the roots are negative, so this will be e power minus something here and e power minus something here. So this means that e power minus t, so then if the time is very very high, so it's minus t, so then the x will become 0. And you will see in a minute when we plot this function, so you will see that there is no vibration, but the x will just go to 0 for a very high x. Okay, so another type of vibration is when this zeta is equal to 1. So when zeta is equal to 1, this is what we call is the critically damped vibration. And again, this is very very important vibration, because in this specific case, when zeta is 1, so this means that this thing will disappear. So zeta is 1, so this means that 1 minus 1 will be 0 here, and again zeta is 1, so zeta 1 minus 1 will be 0 here. So this means that the lambda 1 and lambda 2 will become just minus omega n, and again this will become minus omega n. So the roots lambda 1 and lambda 2 are equal, real and negative numbers. So this means that lambda 1 and lambda 2 is just omega n for this specific case. And the solution to the differential equation for this special case of equal roots is given by this function here. So this means that x will become a1 plus a2 t e minus omega nt. So again, this is the same equation, which is the a1 e power lambda 1 t, but here we are just introducing this t here. So we are saying that this is a2t e power lambda 2t, because the two roots are exactly the same. So we are introducing this t here. So this is how you do this in differential equation. And lambda 1 is minus omega nt, and lambda 2 is also minus omega n. Okay, so the motion in this case also decay with x and approaches 0 for larger t. Now because here again we have minus, and the motion is non-periodic, so in this case there will be no oscillation in the body. And in this if this system is excited with an initial velocity or displacement, or both, will approach equilibrium faster than an overdamped system. So in this case, because zeta is equal to 1, so we say that cc divided by 2 omega n is equal 1. So this lambda zeta is equal to c divided by 2 m omega n. And therefore now, because it's a critically damped system, so we representing this by cc, and this cc is equal to 1 here. Zeta is equal to 1, so we can say that this is a critically damped system, or the coefficient of critically damped system. So this cc is equal to this will become 2m omega n. If you move this to this side here, so cc is the critical damping coefficient. Okay. Now if you consider these two motions for this specific example, so if you consider this spring dashpot in mass system, this is the zeta, which is c divided by 2m omega n. Now if you consider this example that m is equal to 1, so if m is equal to 1 here, k is equal 9, Newton per meter. And now if you assume that C is equal to 15, then what you get for zeta, because you can calculate omega n, which is k divided by m under the root. So you can see that for C equal 15, zeta will become 2.5. So this means that it is an overdamped system. And if C is equal to 6, so then you get zeta equal 1. So this means that it is a critically damped system. Okay, so now for an overdamped system, because we know that this was the solution of this damped free vibration. So A1 E lambda 1 T plus A2 E lambda 2 T. Uh, and this zeta was C divided by 2m omega n, and lambda 1 was omega n zeta plus zeta square minus 1 under the root. And then lambda 2 was the same thing but with negative sign here. Okay, now from if you want to plot this x with respect to time, you want to see how this x will change when you change time. So in this equation, obviously we need to know a1 and a2 because these are two unknowns, and these two unknowns can be calculated from the uh, initial condition. So we are given the initial condition, that is at time t equal to 0, x naught equal 30 millimeter and x naught dot equal 0. So this means that at time t equal to 0, the displacement is 30 and the velocity is 0. So if you differentiate this equation with respect to time, so what you get is a1 lambda 1 e lambda 1 t plus a2 lambda 2 e lambda 2 t. Now for these condition, because we are given omega n, we are given zeta, we can calculate zeta from this equation here. So we can calculate lambda 1 and lambda 2. We can put this in this equation here. We can calculate x dot by this equation here, which is just the differentiation of this equation here. And then from, if you put the initial condition here and here, you get the value of a2, which is 0.03 lambda 1 minus lambda 2, and a1 will become 0.03 minus 0.003 lambda 1 divided by lambda 1 minus lambda 2. So you get these two equations here for a2 and a1, and obviously for the given data you can calculate lambda 1 and lambda 2, so you means you can calculate a2 and a1. So if you calculate this a2 and a1 and then you plot this function with respect to time, so you get this plot here. So this means that if you are increasing time, so the displacement are approaching 0, and as compared to the previous case where the system was vibrating to and fro from the equilibrium position. In this case, when you give this mass some vibration, some displacement, it will just go to its equilibrium position without vibration because of this damping here. Now what will happen in the case of a critically damped systems? Okay, so if you consider this c equals 6, where this zeta is equal to 1, and then for the critically damped system we know that the displacement can be represented by this function here, so which was a1 plus a2 t e minus omega n t. And in this case, if you want to plot this equation here, obviously we want to calculate a1 and a2. So then you will need to find out the velocity, which is the differentiation of this equation. So if you differentiate this equation with respect to time, you get this equation here. And if you put the value of initial conditions, which are these condition here, at t equal to 0, the displacement is 30 and the velocity is 0. So you get a1, which is 0.03, and you get a2, which is 0.03 omega n. So this means that we know everything. The only thing which is unknown is t. So if you put the value of t, you will get x. So if you plot this function for the critically damped system, you will get this response here. So this means that the critically damped system goes to zero very quickly as compared to the over damped system. Okay, now the third case, which is the that is when so that is we explained two cases. That is one, zeta was greater than one, so that was an overdam system, and when zeta was equal to one, this was a critically damped system. And the final case is when zeta is less than one, so this is what we call is an underdamped system. So in underdamped system, if you the because this zeta is less than one, so this thing which was in the roots, which is zeta square minus 1, will become negative because the zeta is less than 1, so is negative. And now if we just recall this thing here, that ea plus b equal eb ea eb. Okay, so then we can write these equations in this form. And now just we are rearranging this term here. So we can say that it's a1 and ei 1 minus zeta square omega nt, and plus a2 e minus I 1 minus zeta square omega nt, and e zeta omega nt. So we are just writing the previous solution for the damped free vibration in this form here. And this is, we are writing this by just using this equation here. And here we are also introducing this I. So I is mean that we are just taking minus 1 common here, and the reason is because the zeta is now less than 1, so to make sure that we don't have a negative sign here, so we are just changing it. Okay, so it's convenient to let new variable omega d, which represent the combination of this omega n1 minus zeta square. So now instead of this whole thing here, if we represent this by omega d, and we also represent this by omega d, so what will happen is that if you change this by omega d, so you will get a simplified equation here. So x will become a1 e I omega dt plus a2 e I omega dt, and e minus zeta omega nt. So you will get this equation here. Now in addition to this equation, we know from mathematics a formula, which is what we call is Euler equation or Euler formula. So which is E plus minus ix, which is iota x, equal cos x plus minus iota sin x. So we have these two iota functions now. So one is here, which we can represent in this form, and another is this one, which again we can represent in this form here. So you can see that this the first function, which is a1 ei omega dt, so which we will represent in this form here, so which will become cos omega dt plus I sin omega dt. And similarly this function will be represented by cos omega dt minus, because it's a minus here, so it will minus here, so minus here I sin omega dt, and then e minus zeta omega nt. Okay, now we have cos here and we have cos here, so we can say that a1 plus a2 cos omega dt here. And similarly we have sine here and we have sine here, so we can see that I a1 minus a2 sine omega dt here. Okay, so now if we just, because a1 plus a2 is another constant, which is a combination of constant, so which is another constant, so we don't need to write a1 plus a2, we can replace this by a3. So cos omega dt, and then you have plus, so this I, so I is just minus 1 under the root, and a1 minus a2, so which is again this one, you can call this as another constant, which is this a4 here, and then with sine omega dt and e minus zeta omega nt. So finally, we are just representing this a3 by this and a4 by this. Okay, now this is the final solution of that particular equation. But as we know from the previous lecture that this equation again consists of cos and sine. So it may be more convenient to change this equation by just a simple one sine or cosine function. So what we are doing here, that we are just changing this equation by this c sine omega dt plus this psi angle here and e minus zeta omega nt. Now this is just a simplified representation of the previous equation, or you can write it in this way here. So ce minus zeta omega nt sine omega dt and plus psi here. And you can see this is how you represent this equation. So again, if you consider this data, which is, you can see that m is equal to 1. So if this mass is equal to 1 kilogram, k is equal to 36, and c is equal to 1 Newton second per meter, so zeta will become 0.08. So this means that zeta is less than 1, so it is an underdamped system. And if you consider these initial conditions, that at time t equal to 0, if you consider these conditions here, we can see that this x is obviously a combination of two functions. One is this decaying function, and one is this sine function. So this decaying function means that it is because minus e power minus zeta omega nt, which this means that if the time is very very large, so this term will goes to 0. But again, we have here a sine function. So this means that if you multiply these two functions, this will become a decaying sine function, which you can represent by this thing here. So in this case, for example, if you want to plot this function with respect to time, so if but obviously you need to know the value of c and the value of this psi here, and which you can calculate from the initial condition. So x is equal to ce, this is the solution, and you can calculate x dot. So x dot means if you differentiate this equation with respect to time, you end up with this equation here. And if you use the initial condition, you get c, which is 0.03 sine psi, and then you can calculate the value of this psi from this equation here. So if you know psi, you know c, so then you can calculate this equation to plot x with respect to time. So you get this red curve here, so which is a decaying sine function. So this means that the motion, the body is now having some vibration, but the vibration is reducing with respect to time. And in this case, again, you can see that this black line here is this term here, so ce minus zeta omega nt, and then you have a sine function, and then this is a decaying sine function, obviously. Yeah. Okay, so this is an exponentially decreasing harmonic function as shown in the figure for specific numerical values. The frequency omega d, so this is omega d is what we call is the damped natural frequency. So and this is so from here to here this is omega tau d, which is the time period of this damped vibration, and which you can calculate from this value here. So finally, in this figure, you can see that we are comparing all the possible type of vibrations. So if we have so the thing is, if zeta is equal to 0, then there is no damping. Okay, and you can see that that we will have this plot here. So for this zeta is equal to 0, there is no damping, so the motion will vibrate forever. The second thing is when we have an overdam system, which is this plot here. So this means that um, the response of the system is going to zero for a very when the time is very high. For a critical dam system, the when zeta is equal to 1 here, so the response goes very quickly to 0. And for an underdamped system, which is this dotted plot here, so it's a decaying sine function. So this means that the system is vibrating, but the vibration amplitude is reducing with time. And again, we can see that for the undamped vibration, the distance from here to here is what we call is the time period for the undamped free vibration, and the we can calculate it from this equation here. So 2 pi divided by omega n, and similarly this is the time period for the damped free vibration. Okay, so if I summarize what we did in today's lecture, so um we said that in many practical systems, the vibration energy is gradually converted to heat and sound, and this is because of the damping in the real world problems. And then we discussed three type of damping. So the first one was viscous damping, which we use mainly in our formulation. And then we also discussed about the Coulomb or dry friction damping, and we also discussed about the material or solid or hysteretic damping. And finally we talked about the damped free vibration. So this is the schematic diagram for the damped free vibration. So it consists of a mass, a spring, a damper, and this is the free body diagram. So then in addition to the spring force, we also have a force for the damper, and we said that the damping force is directly proportional to the velocity, and it is negative because it is opposite to the velocity. And the c is what we call is the constant of proportionality here, and this is the damping constant here, which is, you can see in this case here. Okay, and if you want to write the equation of motion, you will need to use this free body diagram, and using the Newton second law. So you have minus kx minus cx dot equal mx double dot, or you can further simplify this equation, and this will be the final simplified equation here. So in this equation, in addition to the natural frequency, we also introduce this another parameter, which is zeta, and which is the combination of c, m, and omega n. And the unit of the zeta have no units, so it is a dimensionless parameter. And then based on zeta, we classify the damped free vibration into three type. So that is zeta is greater than 1 is what we call is an overdamped system. So for overdamped system, the solution of the dynamic system is this one. So a1 e lambda 1t plus a2 e lambda 2t, and this lambda 1 and lambda 2 can be calculated from the characteristic equation. So these are the values of the lambda 1 and lambda 2, and we know that for if the zeta is greater than 1, then the roots or negative, real, and distinct. So then the solution of the equation will be just this equation here. Another case which is possible is when zeta is equal to 1. So this is a critically damped system. For critically damped system, because zeta is 1, so then this means that this term will be 0, and also this term will be 0. So then the then the lambda 1 and lambda 2 will be so lambda 1 will become equal to lambda 2, which is become minus omega n. And then for if the roots of the characteristic equation are exactly the same, so then the equation of the motion is represented by this equation here. So you have to introduce this t here, so a1 plus a2 t e minus omega nt. So omega nt is the root of the characteristic equation here, and because zeta is equal to 1 here, so that's why we represent this c by cc, which shows that it is the coefficient of the uh, critical damper, and this 2 omega n is equal to 1, so this means that cc is equal to 2 m omega n. And finally we discussed about the underdamped system for which the zeta is less than 1, and for this underdamped system the solution is represented by this function here. So this is actually a decaying sine function, because this is a decaying function and this is a sine function. So when you multiply decaying function with sine functions, you end up with a decaying sine function. And in this equation you have zeta, you have omega n, but you also have these c and you have psi, which are two unknowns, which you calculate from the initial condition. And finally you have the omega d, which is the frequency of the this underdamped vibration. And we saw that this the in the underdamped case the system will vibrate, but the response of the system is reducing with time. And finally we can calculate the time period for this damped vibration, which is obviously 2 pi divided by omega d. And if you put the value of omega d, which is omega n 1 minus zeta square, so which you can calculate from this equation here. So thank you very much.